All right, when you learned about x squared equals 1 and you have to solve a little equation of x squared equals something, how do you do it? Okay, so square root of x squared equals anything else that you should remember to do?
Radical. I'll do it on both sides.
It's one other thing.
X, wait, never mind.
How many solutions does this have?
Plus or minus.
Plus or minus, very good, plus or minus. So you have plus or minus, so we have either one, positive 1 or negative 1 are a solution. So we have 2 square roots of 1. Okay, now x to the 4th. Do we need to do plus or minus for a 4th root?
Yes.
Yes, because why?
Because 4 is even number.
Because it's even. Because it's even, I also need to do the 4th root plus or minus the 4th root, which gives me 2 solutions of positive 1 and negative 1 again. Now I want to ask a question. Can you think of any other numbers that you would raise to the 4th power and get 1? Can you think of any other numbers that you would raise to the 4th power and it would equal 1? Like perhaps a number you learned about yesterday. I. Very good. I. So I is another solution. Can you think of another one that might be another solution?
-1.
I already have -1.
1.
I have 1.
I square.
No?
Negative I.
Negative I. Because if I raise a negative number to an even power, it makes it positive. So just like I squared is, I to the 4th is 1, negative I, the quantity, to the 4th power would also be 1. So there are actually 4 solutions to this. So we can say that it has 4 4th roots. Okay, now, when we get to x cubed equals 1, do I do plus or minus for that?
No, you don't.
Do not. It's an odd root. So if I say the cube root of x cubed is just going to be the cube root of 1, which is 1, because if I do plus or minus, -1 cubed is not positive 1. -1 cubed is still -1. So I can't use that. You could probably guess a few other numbers, but there's really no way to guess the fact that there are really two other roots. There are 2 other roots, but they are both complex and impossible to find unless we do what we're going to learn to do today, which is use the polar form of the number to find the roots. So I'm going to put a little question mark. What are they? We do not know. In general, every complex number has nth roots. And for the most part, we can only find those roots by writing the complex numbers in polar form instead of rectangular form. Now, I was able to kind of guess what the ones were for the 4th root of 1, but most of the time we're not going to be able to guess like that. So how do we find the roots of a complex number? You have to remember a formula that you saw in the worksheet yesterday. Recall the formula for the power of a complex number in polar form. And this was, if I take my complex number and raise it to the nth power, z to the nth, it's the same as if raising r to the n power, cis, and then multiply theta times n times theta. So there's the little formula for taking the power of a complex number. Then we just need to remember that a root can be written as a power. So if I take the nth root of z, that's the same as z to the what power?
-2n.
To the 1 over n.
1 over n. Good. Z to the 1 over n. So I can write that as r to the 1 over n cis 1 over n times theta. So this allows me now to use that same formula to take the nth root. But this only gives me one of the roots. So now I have to figure out how do I get the rest of the roots. So this is how we do it. Z to the 1 over n, and this is de Moivres theorem. This is actually, de Moivre is a French mathematician, and it's kind of an odd pronunciation, but that's how you pronounce it, de Moivre. Okay, z to the 1 over n is r to the 1 over n cis 1 over n times theta plus 2 pi k, where k can equal 0, 1, 2, etc., all the way up to n. Actually, not up to n. Just put 1, 2, 0, 2, etc. It's actually n minus 1. So what this tells me, whatever my original angle is, the first root's found by just using the original angle. The second root's going to be found when I add 2 pi to the original angle. Now, when I add 2 pi to an angle, what does it change about the angle? If I add 2 pi, so here's my angle, I add 2 pi to it, or no, this way around. The same angle, right? If I add 2 pi, same angle. So what I'm going to do is rewrite my angle several different times by adding multiples of 2 pi to it. And that's going to allow me to get the additional roots that I need. So we're going to look at an example of this. It's easier to see with an example. So we're going to look at the example of finding the cube roots of negative 27. In other words, I want to find all of the solutions of the equation x cubed equals negative 27. So the traditional way we've done it is you take the cube root of both sides of the equation. And do you know what one solution would be?
Negative 3.
Negative 3. However, there's two other solutions that we're not going to be able to find unless we do it in polar form. Here. Okay. The first thing we want to do is think of where negative 27 is on the real complex plane. So I want you to remember that we have positive real over here, positive imaginary, negative real, and negative imaginary. So the positive real will correspond with the angle 0. The positive imaginary will correspond with pi over 2. Negative real is pi, and negative imaginary is 3 pi over 2. So when we write a complex number in polar form, if we only have a single number, either real or imaginary, it's going to correspond to one of those 4 angles. If it has 2 numbers, an a plus bi, it'll be in one of the quadrants. So right now we have negative 27. Negative 27 is over here in the negative real direction. So that tells me I have a radius of 27 along with an angle of pi. Does that make sense to you guys? An angle, negative 20, a radius of 27 with angle of pi, because our R value is always going to be positive. So I'm going to call this 27 cis pi. Now some of you are going to follow the notes later on and slavishly think that I always have to put pi here. No. R is going to be positive, but the theta can be all different angles, okay? So R and theta depend on my original number, and then once I have my original, so this is my original angle this time, but in another example, I might not start with pi. I might start with 0 or pi over 2 or some other angle, pi over 3 or some other angle. So just realize that this is my starting point for this particular example. So when I do z to the, so that's my z value, my complex number. So z to the 1/3 in this case is going to be r to the 1/3, 27 to the 1/3, cis 1/3 times pi. So my first example, I don't add 2 pi. I just start with my original angle. And that's going to give me 3 cis 1/3 of pi, pi over 3. Does that equal negative 3? 3 cis pi over 3? Pi over 3 is out this way. Is that going to equal negative 3? Cosine of pi over 3, sine of pi over 3? No, it will not. 3 cis pi over 3 is in quadrant 1. That is not going to give me negative 3. But that's going to give me one of my complex numbers that are the roots. Now I'm going to add pi to my original angle. So in my formula, this is the same as k equals 1. This was k equals 0. Now k is going to equal 1. I'm going to add 1 increment of 2 pi. Yes?
Why were you saying that it was in quadrant 1? How do you know that?
Because pi over 3 is a quadrant 1 angle.
Okay.
So that means that it has a real part and an imaginary part to the number. And so it can't, then this can't be the number negative 3. It's going to be some number in the form a plus bi. So 27 to the 1/3 cis. Now I'm going to say 1/3 times pi plus 2 pi. So take my original angle, add 2 pi, which of course gives me 3 pi. So this is going to be 3 cis, 1/3 of 3 pi is pi. Does that make sense to everybody, where I got that? So I took pi plus 2 pi gives me 3 pi, 1/3 of 3 pi is pi. Now this number is right over here, 3 cis pi. So 3 cis pi, that is my number, -3. So this one, that's the -3. That's the one I already know that I should get. Now I need, yeah, go ahead.
If the number that you got was -3 and the equation is 1 over n, why would it be -1 over 3?
Okay, for the third root, we're going to have z to the 1/3 is equal to 27 to the 1/3 cis. Now I'm making the k in my formula 2. So in other words, I'm adding 2 times 2 pi. I'm going to add 4 pi this time. So 1/3 times pi plus 4 pi, which is the same thing. This is 5 pi. So I'm going to say 27 to the 1/3 cis. 1/3 times 5 pi is 5 pi over 3. So these are my 3 roots in polar form. 3 cis pi over 3, 3 cis pi, and 3 cis 5 pi over 3. And I want you to notice that because I'm taking cube roots and I'm always multiplying by 1/3, and each time I'm adding 2 pi, notice that each of these is 2 pi bigger than the other. So pi over 3 plus 2 pi is pi, plus another 2 pi over 3 is, pi over 3 plus 2 pi over 3 gives me pi. Pi plus 2 pi over 3 gives me 5 pi over 3. So they're always going up by 2 pi over 3 each time. And that's, you'll notice that kind of pattern when you do these. Now let's put these into I've got one more step here. What happens if I add 2 pi one more time? Because I've told you that there's only 3 roots. Here's root number 1, number 2, and number 3. So what happens if I do this process another time? What do I get? What do I get? What happens? So I think I'll go back to what I started with. You guys are so smart. 27 cis 1/3 of pi plus 6 pi, which is 1/3 of 7 pi. So this is 7 pi here. So this is 3 cis 7 pi over 3. And 7 pi over 3 is the same as 6 pi over 3 plus pi over 3, which is the same as 2 pi plus pi over 3. So in other words, I've gone all the way around the circle and back to pi over 3 again. So 7 pi over 3 and pi over 3 are the same thing, so I'm back to root number 1. And if I added pi again, I'd be back to root number 2, and so forth. Now, what we're going to do next is to put all of these into rectangular form and then do some checking on the calculator to see how this works. So far we have 1 root we're familiar with and 2 roots that we're not familiar with. So let's see what they look like in rectangular or a plus bi form. Yes? All right. So let's recall what cis means. Cis means cosine plus I sine. So this says 3 cosine pi over 3 plus 3 sine pi over 3i. So the 3 cosine pi over 3 tells you the real part of the number, the a, and the 3 sine of pi over 3 tells you the imaginary part, or the b, in your a plus bi form. So if I were to graph this little number, it would look something like this. Here would be my pi over 3. This would be a 3. And I could, so this is actually, this is based on a 30, 60, 90 degree triangle. This is a 60-degree angle here. This could, if I look at this in terms of its special triangle, this would be a special triangle where the adjacent side is 1, and the hypotenuse is 2, and the opposite side is square root of 3. And so I could say cosine of pi over 3 is 1/2, and sine of pi over 3 is square root of 3 over 2. And I could actually calculate this without a calculator pretty easily, but I'll also show you on the calculator. So this is the same thing as saying 3 cosine of pi over 3, which is 1/2, plus 3 sine of pi over 3, 3 sine of pi over 3, which is square root of 3 over 2i, or 3/2 plus 3 square root of 3 over 2i. So this is what this number is. I'm saying this is one of the cube roots of negative 27. So let's do a little bit of work on the calculator and show you how you would do this on this part on the calculator. Is it okay if I switch to calculator? Don't know if everybody's done writing. Okay, I want to let me clear this off so that we can start fresh. Okay, so if I just type in 3 cosine of pi over 3 divided by 3, oops, that was not what I wanted to do. Okay, divided by 3, and then plus 3 sine of pi over 3, and make sure that you put the I outside of the parentheses, because we're not taking the sine of I, we're multiplying that by I. So if you've got this, there's my expanded form. Okay, notice there's my 3/2 plus 3 square root of 3 over 2i. So there it is in rectangular form. Now, if I take that number and raise it to the 3rd power, there's my negative 27. Okay, so this is telling me this is actually a cube root of negative 27. Kind of weird, but it is. If I were to multiply it times itself 3 times by hand, I could actually get negative 27, assuming I didn't make any stupid mistakes. Now, I already know that negative 3 is a square root of 27 if I cube that. And then if the third one, let's look and see what the third one's going to be. And you'll always see the nifty pattern, but actually we need to expand this one. This is 3 cosine pi plus 3 sine pi times I. And if you calculate what cosine of pi and sine of pi are, cosine of pi is -1 and sine of pi is 0. So you end up with -3, which is one of the roots that we expected to get. So there's one of my roots, there's another one of my roots. And then the third root, I expand saying 3 cosine of 5 pi over 3 plus 3 sine of 5 pi over 3i. And hopefully you remember a little bit of trig, enough to remember that this has the same reference angle, but it's in a different quadrant. So this is still a pi over 3. I'm still going to get square root of 3 over 2 for cosine. I'm still going to get 1/2 for cosine, square root of 3 over 2 for sine. But I'm not going to have them both be positive now, because 5 pi over 3 is in what quadrant? That's right, it's in 4. Very good. Okay, so this has a pi over 3 reference. This is still 60-degree reference angle, but this is negative, this is positive. So now my cosine value is still positive, but my sine value is going to be negative. So I multiply both of those by 3. So this is my third root right here. And if I raise that to the 3rd power, I will also get -27. You will find that both the polar form of the roots and the rectangular form of the roots follow nice patterns. You will see repetition. And so if you have to find multiple roots, you expect to see that repetition. And sometimes you'll be able to just kind of know what's going to come next. Now, something else for me to tell you about the 3 roots is if I plot these 3 roots in either polar or rectangular form, although it's easier right now to do the polar form, I have 3 cis pi over 3 is one root. And so go out 3 and rotate to pi over 3, and that would be this point right here. Then I have 3 cis pi, so plot one at 3 pi, and then 3 cis 5 pi over 3, so plot the one at 5 pi over 3. And if you were to actually draw kind of a line out to the 3 of them, what do you notice? They look like a rose, exactly. They're evenly spaced like the petals of a rose would be. So these are, the roots are always evenly spaced. Maybe I should spell evenly right since this is an official video here. Evenly spaced. Roots are always evenly spaced. So if I know where the first root is, if I correctly find the first root and I know there's 3 of them, I know where the other 2 are in polar form. It's pretty easy. So you can figure out what angles you need for the other 2. So that's another shortcut. They're always going to be evenly spaced. So if I had 4 roots, they'd all be exactly pi over 2 apart. Or if I have 6 roots, they'd all be exactly pi over 6 apart, etc. Okay, that's it for the roots. So these are the this is what I want you to be able to do on your homework. So if you look at the homework, for each problem, put the number in polar form. So recognize you're going to have a positive radius, and then you're going to have an angle that goes in the correct direction for each of these numbers. When you get to 3 plus 4i, to find the radius, you're going to have to use the Pythagorean theorem, and to find the angle, you're going to have to use inverse tangent. Find all the roots in polar form and plot them in polar form. Then put the roots into the rectangular a plus bi form by expanding out the cis part. And you can do that on your calculator. And then check them by raising them to the power. The 2 most challenging ones would be to find the 8 roots of 1, and that's just because there's more of them to do. And then the second one, on the 4th one, says you'll have to use decimals, so don't round. If you don't round at all, but you just on your calculator go up and grab the number every time you need it, your answer will turn out to be perfectly nice. If you round, you won't get a perfectly nice answer. So I'm just warning you, don't round on that one. Then the last few problems are just a review from a previous worksheet.